So, let us begin lecture 36. We will continue our discussion on polarization, which is part of kinetics of corrosion. Now, there we have seen that this particular equation is a Tafel equation. Beta is Tafel slope and there also we have seen that how this experimental log I applied varies with over voltage. This is the point with I0 and it varies like this. Fine. And at this point I see Mn plus Ne equal to M, and on this side I have preferential anodic reaction, and this side we have preferential cathodic reaction. Fine. So, these were our concept that we have seen in the last lecture, and this neta C is nothing but neta C or neta A, either it could be cathodic over voltage or anodic over voltage, which is due to cathodic as well as anodic polarization respectively, is due to activation polarization. Since we could see that if I have a bulk medium, this is IOHP, this is OHP, and the concentration of CR and CO, and then bulk concentration C, let us say prime, they are on the same plane, and this is distance, and we are seeing that reaction or this particular process is taking place because of the interface jump of ions or atoms over the energy barrier. This energy barrier could be depending on whether it is a anodic current density or cathodic current density, which one is more compared to the other, then this particular plot will rearrange itself. So, then this would be, in this case, this is the situation where we have IC to be more than IA. So, when there is enough supply of cations to this particular plane, so that concentration is flat in the solution side, this is solution side, then the rate at which this interface jump is taking place, that will control the overall potential drop or potential increase or cathodic polarization or anodic polarization, and that would lead to over voltage, either it could be cathodic or anodic over voltage. Now, let us say this at certain point the supply of ions from bulk to the interface to the OHP, and if I say that rate of supply is less than the rate of atomic or ionic jump across the activation barrier, then there would definitely be a lag of metal ion supply to the bulk to the interface. So, there would be a lag from this section to this section, and that lag could be generated because since this rate is increasing. So, that suggests that the current density, which is nothing but a rate, is very high. At a very high current density, there could be a situation, there is a lag of ion supply to the interface OHP for the ionic jump from OHP to the IHP, because when we have this kind of modification in the energy distribution, then we have more of IC. In this case, IC is greater than IA. So, there would be a lag. So, now there could be concentration profile with decreasing concentration as we come from the bulk concentration to the interface. So, this concentration would have a distribution like this. So, here it would become then CO prime. So, this is the interface concentration due to this very high activation, this very high rate of current flow because of this higher rate of ionic jump across the activation barrier. So, that situation we would come across another type of polarization, which is called concentration polarization. This is due to variation in concentration at the reaction front, and that happens at a very high activation current density, very high current density, because if it is a low current density, the rate of atomic jump is little low. So, it can be possible that the rate of ion supply from the bulk would be equal to the rate of ionic jump. So, there should not be any a lag of concentration from bulk to the interface. Now, in this situation, let us look at this concentration polarization in a little depth. So, let us talk about concentration polarization. So, as we are saying that there could be a, so this is IHP, this is OHP, and this is the initial concentration, this is the concentration in the bulk, which is similar to CO, let us say, because the bulk concentration is similar to the interface concentration in the beginning when there was no current supply or the over voltage is 0, and after supply after the current flow, and let us say it is a little bit higher current density. So, then there could be a concentration profile, this is the concentration profile, and this axis is concentration. This is CR, this is similar to CO because the bulk concentration I am considering CO, and let us say this concentration is C, which is the interface concentration. Now, when neta equal to 0 or I equal to I 0, I would get C equal to C 0. The concentration or C 0 equal to, I would say, equal to C 0 or interface concentration. Concentration of metal ion N plus. Now, when neta equal to neta and I equal to I max, let us say, that means if as the current density is increasing, I am getting over voltage, as well as the over voltage is increasing, I am seeing that this particular concentration is going down gradually. So, this concentration profile will keep changing as we increase the current density, and finally it will reach to 0 value. This is 0 0 axis, let us say. So, it will reach to 0 value. So, that means when I equal to I max, I should get concentration should be 0 at the interface. Okay. So, these two are boundary conditions. Now, I know that when I equal to I, so then concentration would be C at the interface, and that time I would get some over voltage. Now, when this concentration is changing from this point to this point, I can apply equilibrium condition and find out potential developed at the electrode because of this concentration change by applying Nernst equation. So, then E equal to E 0 plus R T N F ln concentration of O divided by concentration of R. Now, if I consider that concentration of R is, or in terms of activity, if it is concentration is considered to be 1. So, then I can write it is only dependent on the concentration of ln C 0, and that time the potential I consider to be E 1, and E 2 would be E 0 plus R T N F when concentration is C. So, this I am getting these two equations. So, the over voltage would be E equal to E 2 minus E 1, and this over voltage is due to this concentration change of this metal ion. So, I can put it as concentration, or in short I can mention it as concentration, and this is concentration polarization or over voltage. Now, whenever I have this diffusion or concentration profile, I have a boundary layer thickness, which let us say I consider to be del, which is the boundary layer thickness. This is the del, which is the boundary layer thickness. Now, I can use Fick's first law here, J, which is the flux. I can write in this form moles per unit area per unit time equal to minus d dc dx. I am considering steady state situation here, and this can be when the situation is this and this is C, then the flow of metal ion from this bulk to the interface or bulk to the interface, that rate would be decided by this particular equation, which is the Fick's first law, and we are considering steady state flow. This can be approximated as minus d, dc can be written as del c, and x can be written as del, which is minus d C 0 minus C divided by delta. Now, I know I by NF equal to moles per unit area per unit time. If you go back, if you check, you will see that this is the rate of flow of metal ions per unit area per unit time, which should be equal to J. Then I can write I equal to NFJ. So, I put this particular situation minus NFD C 0 by minus C delta. Now, I use these two conditions. When I equal to I, so that time the concentration difference is C 0 minus C, and when I equal to I max. So, that means that maximum current density where the whatever metal ion is coming from the bulk to the interface, that metal ion is immediately getting reduced and going to the IHP, the or inner Helmholtz plane. At that situation, the concentration at OHP should be 0. So, then C equal to 0 or del C would be then equal to C 0. So, in those situations, let us continue from here. Now, then I can write I max equal to minus NF d C 0 by delta. Therefore, neta equal to or concentration E 2 minus E 1 equal to E 0 E 0, they both will get cancelled. So, that means we are left with NF ln C by C 0. And remember, whenever we try to understand over voltage, we have to always differentiate between initial, final to initial. So, the over voltage should be E final minus E initial. Here this one is the initial potential when the concentration of metal ion at the interface is C 0, and this particular is the final. So, that is what the over voltage is E 2 minus E 1. So, this I can write in terms of NF into 2.303 log, I can have C minus C 0 plus 1, and if I take R to be 8.314, T equal to 25 degree Celsius, that means 298 Kelvin, and F equal to 96500 Coulomb, then I can get 0.059 by N log 1 minus C 0 minus C by C 0. Here I have, sorry, this should be minus. I have just made some modification here. Here it is, I am just adding 1 and then also subtracting 1 from that. So, that is what I am getting this equation, and then this I can write 0.059 neta log 1 minus, I will put this expression. So, in this case C 0 minus C equal to minus delta by NF d I, and here I can put C 0 equal to minus delta I max divided by NF d. So, if we put them, so delta delta as well as this NFT part would get cancelled. So, we will be left with this equation. So, this is concentration. So, this is the expression for concentration polarized over voltage. And as we have said that what is I max? I max is basically the current density. We have explained also at which whatever metal ions are coming from bulk to the interface are getting reduced. So, that means my interface concentration should be 0 when I reaches I max. So, this is another equation. Now, if I try to connect this both this concentration, so this means this is concentration polarization. So, overall polarization should be equal to activation polarization plus concentration polarization. So, I can write total equal to N activation plus N concentration. So, then I can put it as plus so this should be 1 N log 1 minus I by I max. Because when we have overall polarization, if we try to reach to the concentration polarization end, we should go first the activation part and then the concentration part will come up. Because when we have activation part, when we have activation controlled polarization, then I have enough supply of metal ions from the bulk to the interface. So, there is no concentration depletion in that interface. But as we go higher and higher activation polarization, that means as we are going for higher and higher current density, we could see that there will be depletion of metal ions at this OHP as we have seen in the present case, and then we will get to the concentration polarization regime. So, there if we have concentration polarization, then there should be it should start with the activation polarization, then we will reach to the concentration polarization. So, now if I try to plot concentration polarization, which is N concentration is equal to 0.0591 N log of I minus I by I max, where I max equal to minus dNf C0 by delta. So, this plot would look like this. So, this is log I again, this is polarization. Now, when we have 0 over voltage, this is my I equal to 0, I 0, this is basically I 0 value, where the polarization is nil or over voltage is 0, then first concentration polarization will start, and then immediately once we reach to the I max, because I am seeing that the current density is gradually increasing, I would get immediate, because when I reach I max, so this becomes 1, this becomes 1, so this neta concentration would be infinite, the over voltage should be infinite. So, it would be a flat parallel line parallel to the over voltage axis. Until this particular current I max, if I try to plot this particular equation, I would see a plot like this. Okay. So, this is activation polarization, and this part is concentration polarization. And this particular current density for that particular reaction is I max. This is also termed as I L, which is L is nothing but limiting. So, this is I L is equal to limiting current density. Now, here couple of interesting facts is this term as well as this term. Now, if C0 increases, let us say I increase the C0 and I am not changing, other things are remaining same. So, that situation I would get I max should increase. If we do not change d, which is function of temperature, N and F for this particular redox reaction, Hubschel reaction should be same. Delta, if we do not change the boundary layer thickness, so I should have this particular consequence. Now, if I change delta, let us say delta increases, that means delta increase means if we have the concentration profile like this, so then this is my delta. If it increases, let us say if it becomes like this, so that means it increases to this much. So, then as per this equation, if the concentration is not changing, d is not changing, the consequence should be I max should decrease. And how can we change this delta? Delta can be changed if we incorporate agitation. Agitation means if we churn the solution, we would lead to have this kind of situation. Now, if d increases, that means diffusivity increases. As per this formula, this minus sign, remember this minus sign is indicative of flow of ions against the concentration profile. Concentration, this minus sign is basically indicative of flow of ions from higher to lower concentration, and this d increases, I max also increases. So, these are some factors which affect concentration, polarization. Fine. So, let us stop here. We will continue our discussion in the next lecture onward. We would try to connect this activation as well as concentration polarization and get to a concept called mixed potential theory, which will enable us to understand corrosion mechanism in a much better way rather than going through a very analytical path. Okay. So, let us stop here and we will continue our discussion in the next lecture. Thank you.